Good morning, here again for another lovely session of CENG 4412 Steel and Concrete Design. This is going to be a 20-second lecture in the video series, and today we're going to start in this video looking at the capacity of fillet welds. So we're good to go here, and we are rolling, so good. Okay, so previously we discussed some of the theory and of fillet welds, and now I want to move on to discuss some of the actual calculation of fillet weld capacity. So fillet weld strength. Here. Fillet weld strength. So the fillet weld strength is going to be determined by two things. Basically, just like with many things in steel design and other forms of engineering, we're going to take a an approach that you might call the weakest part of a chain is its weakest length, or a chain fails at its weakest point, that kind of thing. So we're going to look at the two different areas where a fillet weld can fail, and that's going to be the overall strength of a fillet weld. So an individual fillet weld can fail in two ways. Now, this is not going to be the overall design capacity of a connection. I'm talking about just the welds themselves. An individual fillet weld, not a connection, but just a fillet weld, can fail in two fundamental ways. One, the weld itself can fail. The weld itself, it fails in shear, or at least what we'll be talking about today in here. Fails in shear, or two, the base metal fails in shear. So in other words, if I have, say, one plate here joined to another plate here, and we remember from last time, these don't have to be literal plates. These could be just structural elements or elements of a shape like a flange, web, etc. If I have a fillet weld here, what could fail? Well, this plate could fail in shear. Basically this section here could tear out. This section here could tear out in this plate, or the fillet weld itself could fail. And so when we analyze the strength of a weld, we need to consider both the fillet weld material itself and the base metal strength. Okay, so let's consider the weld shear strength. We'll look at the formula here, and then we'll discuss it. Weld shear strength, well, phi Rn is going to be equal to 0.75 times 0.75 times, and this is going to be the strength. Oh, let me indicate that this is per inch. The weld shear strength per inch is going to be 0.75 times 0.707 times the width of the weld times 0.6 FEXX. Well, let's discuss this and what this means. Well, first of all, W is going to be the width of the weld. And this would be its narrowest dimension, but we're assuming a 45-degree angle here. I'm assuming a weld that is a isosceles triangle here. So if we don't have that, then we would need to adjust this. But basically, if you think about this, what does this mean? Well, first of all, let's just annotate this. Or let me actually go ahead and say the weld strength overall. If I want to have not per inch, but just overall, phi Rn would be equal to 0.75 times 0.707 times W times L times 0.6 FEXX. So here, but again, let's go down and define these things. So this here, 0.75, this is going to be your resistance factor. It is a fracture failure, so we're going to use 0.75. And 0.707, does that look familiar to anyone? It's what? It's the square root of something, yes. Basically, this should look from, not square root of 2, but it's a the thing, if you remember your trigonometry, 0.707 should just jump out at you as saying, oh, this is something that looks familiar. Basically, if you go, so remember last time we learned that the failure plane of a weld is this? Remember we learned that the failure plane of a fillet weld is going to be along its, again, the failure plane of a fillet weld, or any weld, is going to be along the distance from the root of the weld, along the least distance from the root of the weld to the face of the weld. And if you work through your trigonometry, you will find that length is 0.707 W. That length from here to here, you could apply some trigonometry there and solve for that, and that would be 0.707 W. Basically, this, again, or W is the width of the weld. And so this is the shortest length through the weld. 1 over square root of 2, yes. So this is the shortest length from root to face of weld. W is going to be equal to the width of the weld. Well, actually, let me just say that this, let me show this arrow applying the whole thing here to this 0.707 W and 0.6 EFXX. This is basically the shear strength of the weld material. The shear strength of the weld material. The shear strength of the weld material. Okay, and again we use 0.6 because, well, FEXX, that's going to be the capacity of that filler material in tension. And we multiply by 0.6 to transform it into its capacity in shear. So that's how we calculate the weld shear strength. Next we want to look at the base metal. So weld shear strength per inch and weld shear strength overall. And I should probably put a shear there. Weld shear strength overall. Again, so this is the only difference between this one and this one is I've added an L, which would be the overall length of the weld.
Is that just a different equation?
There are different variations of it, yes. There are different variations of it, yes. Okay. Next, I want to look at the base metal shear strength. The base metal shear strength. Here, let me do per inch first again. Per inch here. Well, here, VRN is going to be equal to the minimum of two quantities. First, 1.0 times 0.6 Fy, 0.6 Fy T, or, and also the minimum of these two quantities basically, 0.7, 0.75 times 0.6 Fu times T. Basically this here is going to be we have a yield failure and a fracture failure. A yield failure and a fracture failure. Here. A yield failure and a fracture failure. let's see here. Here. Huh? Questions? Oh. Anyway, 0.75. Okay. And so all those should be fairly straightforward then. And this is all per inch. Oh, and interestingly enough, though, here, what does this mean now? Well, where? So let's look at this here, though. Your T here, we're using the plate thickness. And the reason for that is if I have a plate and sitting on top of this is a fillet weld, so if the fillet weld is sitting on top of this, if this is going to fail, it's going to fail along this plane here. Otherwise, and if the weld is going to fail, of course, it's going to fail along that plane there. So T is the plate thickness, Fy is the yield strength of the base metal, yield strength of base metal, and Fu is going to be the ultimate strength of the base metal. But again, we see that that 0.6 to transform it from tension to shear of base metal. Here. Now let me double check something here. Ultimate strength of base metal. Let's see. Yes. Okay. Okay. Now, I'm not really on any, I'm just looking at, this is based off of table, well, let's see here. Let me look at the base metal here, J4. J4, I'm not really on any particular page. These are just my own notes. So anyway, but let's see, so. But I'm trying to find where that 1.0 came from. That's the thing that really stands out. So that might have been an older edition of the code. I would need to confirm that. So I would need to double check that. That may have to be 0.75. I'd have to double check that. Okay. Anyway, but that's the basic idea. And in terms of actually calculating this, though, applying this, calculating the capacity of welds, the overall capacity of a weld. And of course, remember that this is going to be per inch. And so if I actually want the FRN, the actual FRN, not just the FRN per inch, but the actual FRN, I would then need to multiply by the actual length of the weld in inches. Okay, so calculating the capacity of a weld. One, calculate capacity of weld material, of the weld material. Two, calculate capacity of base metal. And three, choose the minimum, or the minimum will be the design capacity. The minimum will be the design capacity. Okay, so we have that, and let's see. Okay, so any questions on that? I think that's hopefully fairly straightforward. Now here, let's see. Now let's move on to looking at something else. And this is J2.4 here. Actually J2.6, okay. here. Now, let's consider this here. For simple concentrically loaded connections, or in other words, concentrically loaded connections, concentrically loaded connections, J2.6a, here, AISC J2-6a specifies that the larger of two things will be used. The larger of two quantities will be used. Will be used. And we have this, that Rn is equal to RWL plus RWT. And although they add an N here for here, they add an N here to these terms in the code. NWL plus RNWT. And this is J2-6 1 or J2-6A, or 2. And what this is this is the strength of the longitudinal weld. Or actually, let's back up. Where RNWL is the strength of longitudinal weld, the strength of longitudinal weld, and this is going to be equal to 0.6 times FEXX. Again, that's the strength of the material.
That's RNWE or L?
L. As you can see on page 16.1-124. So 0.6 FEXX times 0.707W times L, basically times the length of the weld. LWL. Now I need to define what this stuff means. So again, W is going to be the width of the weld. Here. Let's see. So this is going to be equal to where, well, LWL. That's a good way to describe that. And RWT, and I know this looks very confusing, but really this isn't that bad when you start actually reading what these things are. NWT is going to be equal to 0.6 FEXX times 0.707W times LW NT, or LWT, where LWL is the length of the longitudinal weld. The length of the longitudinal weld, and LWT is the length of the transverse weld. Okay, and then we also have condition 2. So again, I told you that we're going to use the larger of two things, equation 1, or equation 6-2-6A, or 2, equation J2-6B, which is that Rn is equal to 0.85 times R NWL plus 1.5 NWT. R and WT. But what does this mean? What is the difference between a longitudinal and a transverse weld? Any idea? What is the difference between a longitudinal and a transverse weld? Direction with respect to the axis of the member. Yes, exactly. So, in other words, if you have a, and so this is just two different ways of combining these things together. In other words, if you have, say, one plate here, imagine you have something like this. And you have another plate here. And then imagine you have a fillet weld here. And then all the way around there. This is going to be the length of your transverse weld. So, length of the weld transverse, LWT. And this would be the length of the weld longitudinal, LWL. And you would calculate the capacity of each, and then combine them together using this equation here. Then, let's see. And governed by J4. Let's confirm that. Yeah. Okay. Yeah, I'm still trying to find the origin of that 1.0. That might you might want to use 0.75 for that. I would have to double check that, and that's still bothering me a bit. Okay. Well, let's see here. Where is that coming from? Let's double check something here. And anyway, all right, so any questions on this so far? All right, here. All right, and I think that'll do it for this portion of the video.